So hello again. This is going to be a little unusual session. I was going to be giving this at the SARA Australia Drake's Lounge session tomorrow night, but something came up and unfortunately I have to be elsewhere. So I thought I'd record it and hopefully get it post-processed and posted to the Broward Astronomy YouTube channel before I need to be there tomorrow. So what I'm doing is soliciting for amateur radio astronomy observations of a particular white dwarf. That's the WD. Its catalog identifier is the 0810-353. So the original audience for this topic was the Broward Astronomy session on July 15th. The edited video of that is available for public download at no cost on the Broward Astronomy YouTube channel, and I'll put the link in the details to this video when I post it. This is a shorter version of that presentation. Like I said, it was originally targeted for Society of Amateur Radio Astronomers, July 21st, 2023 Australian Drake's Lounge online session. Since the specific target I'm looking for is in the Southern Celestial Hemisphere, Australia seemed an appropriate audience. The goal of this presentation is to solicit observations, specifically amateur radio astronomer observations. Unfortunately, a personal issue has come up and I need to be elsewhere at the time of that session. I'm willing to schedule something in the future. So here's a little bit of overview of what is a white dwarf. You can see sort of at the top center a sun-like star, that's like our sun. Towards the end of its life, it will become a red giant and then not supernova, but go into a planetary nebula, casting off shells of material and shrink down to a white dwarf. A much more massive star would become a red supergiant, go supernova, and then either shrink down to a neutron star, we know it as a pulsar in radio astronomy, or as a black hole. So you can see the distinctions of white dwarf versus neutron star. But as we're finding out, as we observe more, as we improve our instruments, what we used to think of as a small number of points along a curve, we're starting to find midpoints along that curve. And in particular, if you think of neutron stars, we found neutron stars with strong magnetic fields. We call them magnetars, or the next step on from a typical neutron star before it gets to a black hole, a quark star or a strange matter star. And I did a presentation on that one. But specifically, we'll be looking at a white dwarf that is less than a neutron star, but more than your typical white dwarf, as it is highly magnetic, it's pulsating, and it has a slow rotation, unlike a neutron star, which has a fast rotation. This particular stellar remnant white dwarf is WD 0810-353. So detectable emissions from white dwarfs, typically we'll see white dwarfs categorized as either singular or in a pair with another star. In 1917 was our first observation of a singular non-binary white dwarf. They're typically captured in survey observations because they're not all that bright or exotic and don't have a lot of nebulosity around them. The white dwarfs that we catch in pairs are due to a white dwarf drawing stellar matter off of usually a red giant next to it in orbit with, in a pair with it. The counter to that is something we found in 2016, AR Scorpii and Scorpius. We found it emitting X-ray through radio and at a very slow rotation period of 3.56 hours. It was believed to be a gradually spinning down white dwarf with a sizable magnetic field. This particular target that I'm soliciting observations for is a singular. It's roaming out on its own. It's typically categorized as a rogue, and it's on a course towards our solar system. Its pulsation emissions in all varieties of wavelengths have yet to be categorized as to specific bands and flux, or density of photons per area. So here's the sort of one slide describes it all. The particular white dwarf is in the constellation Puppis, which won't be viewable from South Florida where I am until October, but I'll look for it then. But in the meantime, for those folks down in the Southern Hemisphere, you should be able to see it more easily. It originally showed up in the Gaia catalog from the European Space Agency, and it was released in Data Release 3. There's a nice long number for the Gaia catalog in it. It's only 36 light years away. That's measured as of 2017, but as I say, it's heading towards us. It's smaller than the sun. Its radius is well less than the sun because it's a white dwarf, it's denser. Its brightness is only magnitude 14.5, so you're not going to see it naked eye or with a small telescope. It has an amazingly intense magnetic field, 30 million Gauss or 3,000 Tesla, which is about 1,000 times more than your typical 3 Tesla MRI machine would be. Because it's coming towards us, the light from it is blue shifted, and because its magnetic field bends things, it's not clear as to how fast it's approaching us. It could be 80 kilometers per second, 378 kilometers per second, or 4,448 kilometers per second, because we take different measurements and we came away with different calculations. As of now, it's expected to traverse our Oort cloud at the edge of our solar system, but given its mass and how fast it might be moving, it's not expected to hit anything or scatter anything in the Oort cloud. So fingers crossed, nothing going to hit anything at this point. But what makes it noteworthy is not its diameter, its mass, or its luminosity. It's kind of a smallish white dwarf. Not specifically its radial velocity moving towards us. Might pass into the Oort cloud anywhere from 29,000 to millions of years from now. So that's not an issue. But we do need a better calculation on its velocity accuracy towards us. Like I said, it's expected to traverse the Oort cloud at about 1.5 light years from Earth. It's a dwarf star. It's small. Oort cloud is large. Oort cloud is not that dense. Given that it was once a star, might have had a solar system, it might be dragging some things like debris or asteroids or comets, or maybe even planets, but that's not yet determined. The concern is the electromagnetic emanations from it. It doesn't have to have the gravity or mass of a neutron star. It could have a broader width beam, broadband electromagnetic emanations. Its rotational period is expected to be about 1 minute. The sun's rotation is about 24 days, so it's slowly rotating. Think of it as a slow-moving lighthouse. Your typical pulsar or neutron star is going to be rotating in tiny fractions of a second. The slow rotation should make it easier to spot, more easy to spot than your typical sub-second pulsars or your fleeting fast radio bursts. And it's not shrunk down to the size of a neutron star. It's bigger than that, which means it's going to be not rotating very fast anytime soon. So the emissions by typical white dwarfs are soft X-ray, ultraviolet, visible infrared, and some radio. The actual wavelengths for this specific white dwarf need to be evaluated. It might repeatedly bathe the Earth in its radiation as it approaches, traverses, and then departs from its interactions with our solar system. Given that, if its emissions are at significant wavelengths or energy levels, then it could start impacting us many years before it ever gets to closest approach, and it could continue to impact us many years after it traverses and passes away from us. The high magnetic field could further energize its emissions or concentrate them. I'm hoping that it's a plane of emission. The angle that the lighthouse is putting out a beam at is not in line with our solar system's plane of rotation. More, if we could have it 90 degrees to it, that would be great. If it's not, and if it's synchronized its rotation with the Earth's rotation and our movement around the sun and the direction of rotation, then this is something we need to take a look at. I'm not a big purveyor of fear, uncertainty, doubt, or FUD, but I think it needs to be categorized and monitored long term. We have several instruments up there. If it's producing gamma, that's the highest energy, integral, swift, and Fermi. If it's producing X-rays, we've got Chandra Archive and XMM Newton. It is known to be producing an ultraviolet, so we've got the Hubble Space Telescope and some other instruments. Infrared, not so newly anymore, but the recently launched James Webb Space Telescope or the Webb. We have survey images in optical. from the 2MASS catalog, and you can find those in SIMBAD or VizieR. The Russian Radio Astronomy Observatory out there in space, Spectre RG, could sign that up to get some observations. But in particular, this solicitation is for ground-based radio observatories, in particular the amateur radio astronomer community. So it has yet to be fully characterized in all the possible wavelengths. The Space Telescope Science Institute archive includes infrared, visible, and ultraviolet data from photometric as well as optical surveys, and some spectroscopy from the International Ultraviolet Explorer. And you can look it up either by its J number or by its white dwarf identifier. I searched a number of other catalogs, could not find it listed as either radio frequency or high energy X-ray or gamma. In SIMBAD, here's NED, NRAO. Cambridge, I looked through 2C down through 8C, couldn't find it. The Arecibo historical data, PALFA, couldn't find it in there. And the Parks Catalog 90, couldn't find it in there. I'm guessing that they presumed that it's your typical white dwarf, nothing much to see in radio, although the fact that this is more compact than your typical white dwarf, is spinning, has a high magnetic field, I'm suspecting it's going to be producing radio emissions, much like a pulsar would. So I'm looking to the professional and particularly the amateur radio astronomy community, initially for ad hoc observations. Can you actually detect it? And then more characterization as in what bands do you see emissions on, and what levels of luminance at your particular observatory. And since it's not yet categorized, that means that anyone with a receiver, regardless of the band, can take a look at it. We already know that certain types of pulsars emit radio frequency over a very large number of bands. So even though we've got observatories that look in specific bands, that doesn't mean it's not emitting in other bands. It's just that's all the instruments they have. And the same thing in this particular case is observing what you got. Now, the emission beam characteristics of your typical pulsar are narrow and intense, and they're typically far enough away from Earth that we don't really care. They're rapidly rotating. This thing is going to be traversing our Oort cloud, so it is eventually going to get within about 1.5 light years of Earth. It may be that its beam width may be much wider and it's much slower rotating. If you think of a neutron star as kind of an X-ray laser at a very long distance, this thing is more like a broadband flood lamp that's close to us. It'll be approaching for thousands of years, traversing for maybe hundreds of years, and then departing for thousands of years, all of which it's going to be rotating and lighthouse swathing us in whatever emissions it has. Don't know what its emission power is. Is it going to affect us at all? Given that it's only 1.5 light years away and it is producing emissions, it will have some effect. Hopefully it's not catastrophic, but we won't know. So we need to start observing this thing in all wavelengths and monitor it. Who knows? Maybe we'll just get an interesting light show from it. Zodiacal light could be bright enough to see in the daytime. Who knows? But we'll never know until we actually take a look at it, until we confirm its characteristics, confirm that it is on approach, how fast it's going to be arriving, and what its traversal path is through the Oort cloud, or closer maybe, don't know. Further would be great, but until we know, we need to determine the magnetic field strength to know how that's going to affect either the concentration or the energy levels of its beam. So we need to know the beam rotation period, the angle of rotation versus the Earth orbital angle around the sun, the sweep direction. In other words, if it's, think of two cars, if it's one's coming at and the other one's going away, then the contact point is going to have higher energy level. We need to determine the diameter of the beam as it reaches Earth under all these circumstances of approach, traversal, and then through departure. And we need to look in whatever bands we can look at. Radio for this community, but also we need to get some other folks taking a look at it. And we need to determine the specific flux or luminosity in those bands to judge the level of impact. So you might say, why am I, an individual amateur in optical and radio astronomy, soliciting for these observations? Don't we have government organizations looking out for us? Yes, given that they realize near-Earth objects might have a potential threat to the Earth, the U.S. Congress directed NASA to observe, catalog, and categorize the impact potential of such objects. And there's an organization within NASA called the Planetary Defense Coordination Office, PDCO. They've categorized 30,000 plus, and they're doing about another 500 per year. But these are all collision impact focused. They do not consider irradiation by things that are coming closer, transiting our solar system. So this would be a new category of potential threats. And don't think we want to wait until Congress comes back around and the light bulb goes off and says, yeah, we got to look at those too. We have a slowly rotating, pulsating stellar white dwarf. It's a remnant of an original star that's now towards the end of its life. It needs to be recognized as something that should be characterized and its threat potential evaluated, even if only we get what we only get from is a light show. But also realize that if it was a threatening emanation, then we currently have no defensive technology against intense or long repeated pulsar-like electromagnetic radiation on the Earth. Sure, we have an atmosphere, but it's only going to be good up to a certain level. So in conclusion, whenever you think you've got a good beat on things and then you improve your instruments or you look more often at more things, additional points along that curve are going to show up. And in this case, this is the stellar degeneracy curve. As you know, we go from stars into white dwarfs or pulsars or neutron stars onto strange matter stars onto black holes. So we're finding more points along that degeneracy curve. This was first reported as your typical white dwarf until they found out the level of magnetic field and the fact that it was rotating slowly and it's headed our way. We need to take a look at this. And we need to be looking at more than just collision avoidance kinds of stuff. Electromagnetic emanations can be hazardous to us as well. We need to be observing with whatever technologies we have available at our disposal, whatever instruments and observatories. We need to kind of remove the blinders and broaden our vision to look in whatever capable wavelengths we have for all sorts of threats. Maybe if somebody in political circles sees this video or is a member of SARA in the US or in Australia or elsewhere, they could go like, maybe we ought to have the NASA PDCO take a look at conceptually, should we be looking for these things? And if they do, then, maybe we will reevaluate things. If you remember back to the beginning of the 1900s, Andromeda was thought of as a nebula. And then we looked with better cameras, imagers, bigger telescopes, and we went, wait a minute, that should be a whole new category of things called galaxies. Just when you think you've got a good beat on things and you know how everything's going to be, as your observing improves, your instruments improve, you look more often, you might have to recategorize things. And for those that are interested, that's about me. And then as usual, I have a lot of links, and I will put these links for more information into the description of this video when I post it. And if you watched it all the way through to the end, thank you. If you like this kind of thing, you can go back to the Broward Astronomy YouTube channel and look for more stuff. If you want to know when new things are posted, you can either subscribe and set notifications, or you can go to Facebook and follow us at Broward Astronomy on Facebook. And thanks.